What's up guys, this is Massey. Welcome to another video. In this video I want to talk about Arrhenius equation, and the equation we have here is K, which is the rate constant in the reactions. That's equal to A, which is frequency factor, times e to the power of negative EA over RT. What is EA? EA is activation energy, R is the gas constant, and T is temperature in terms of Kelvin. We can also show this equation in logarithmic form, which we have it in this form here. I derived you how to get from here to here. We just divide both sides by A, so it's going to be K over A equals to e to the power of negative EA over RT. Then we take ln of both sides, is going to be ln K over A. Ln and E cancels out, is going to be negative EA over RT. Then ln K over A is going to be ln K minus ln A equals to negative EA over RT. Then we're going to have ln K equals to negative EA over RT plus ln A. Then what we can say here, we're going to end up having a linear equation. Y equals to mx plus b. It means that the dependent variable is ln k, the independent variable is 1 over t. So when we graph ln k with respect to 1 over t, we're going to have a straight line, and the slope is negative EA over r. That's the slope, and the y-intercept is ln a. Using this relationship, we're going to find out the relationship between the rate constant and temperature. So for different temperature, we can estimate the value of rate constant. Usually, for larger values of temperature, we're going to have larger values of K. Then when we compare two of them, we can say two different temperatures and two different rate constants. We can say ln Ky1 equals to negative EA over RT1 plus ln A. Ln K2 equals to negative EA over RT2 plus ln A. When you subtract it, it's going to be ln K2 minus ln Ky, and these two, subtraction these two cancels out, and when we simplify, it's going to be ln K2 over K1 equals to EA over R times 1 over T1 minus 1 over T2. Remember, T is in terms of Kelvin, and R is 8.314 joule per Kelvin per mole. Let's see some example. Determining activation energy. The reaction 2N2O5 in gaseous phase gives us 4NO2 plus O2. Was studied at several temperatures, and the following values of K were obtained. So based on different temperatures, we got different rate constants. Calculate the value of EA or activation energy for this reaction. So in order to do it, first of all, we need to convert temperature in terms of Celsius to temperature in terms of Kelvin. So I'm going to have temperature in terms of Celsius. We have 20, 30, 40, 50, 60. Then we change it to temperature in terms of Kelvin. So we add 273. It's going to be 293, 303, 313, 323, 333. Then what we need to do, we need to inverse it. So based on the formula we had in here, we need to find out the inverse of the temperature. So that's going to be 1 over T, which is going to be 1 over 293, which is 3.41 times 10 to the power of negative 3. 1 divided by 303 is going to be 3.30 times 10 to the power of negative 3. 313, the inverse of it is going to be 319 times 10 to the power of negative 3. The inverse of 323 is going to be 3.10 times 10 to the power of negative 3. And the inverse of 333 is going to be 3.00 times 10 to the power of negative 3. Then we have the K values, 2.0 times 10 to the power of negative 5, 7.3 times 10 to the power of negative 5, 2.7 times 10 to the power of negative 4, 9.1 times 10 to the power of negative 4, 2.9 times 10 to the power of negative 3. Then again, based on this formula, we need to change it to ln k. Find out ln k value, and then we can graph it. Ln of all these numbers, so it's going to be negative 10.82, negative 9.53, negative 8.22, negative 7.00, negative 5.84. So we need to graph ln k with respect to 1 over t, as you see it here. So when you graph such a thing, ln k with respect to 1 over t, it's going to give us something like that, straight line like this. And then we can find out the slope. The slope is going to be change in ln k divided by change in 1 over t. When you calculate it, that's going to be negative 1.2 times 10 to the power 4. And the slope has to match with the expression we had in here. The slope is negative EA over R. So it means that negative EA over R equals to negative 1.2 times 10 to the power 4. So EA will be 1.2 times 10 to the power 4 times R. R is 8.314. So that's going to give us 1.0 times 10 to the power 5. And the unit will be joule per mole. Joule per mole is going to be the unit for activation energy. Let's see another example. The gas-phase reaction between methane and diatomic sulfur is given by this equation. Methane plus 2SS2 is going to give us CS2 plus 2H2S. At 550 degrees Celsius, the rate constant is 1.1 liter per mole per second. And at 623, the rate constant is 6.3 liter per mole per second. Using these values, calculate EA for this reaction. So we can say, based on the formula we got in here, ln K2 over K1 equals to EA over R times 1 over T1 minus 1 over T2. So that's going to be ln K2 over K1 EA over R 1 over T1 minus 1 over T2. Before doing that, we need to convert these two temperatures into Kelvin. 550 plus 273, and this one 625 plus 273. 550 plus 273, that's going to be 823. 625 plus 273 is going to be 898 Kelvin both. So let's put it there. This ln K2 is 6.4, K1 is 1.1 equals to EA over 8.314, 1 over 823 minus 1 over 898. So ln 6.4 times 10 divided by 1.1, that's going to be 1.761. Let's find out this part. 1 divided by 823 minus 1 divided by 898. That's going to give me 1.0148 times 10 to the power of negative 4. So EA over 8.314 is going to be 1.761 divided by 1.0148 times 10 to the power of negative 4. That's going to give me 17353.17. So EA will be 8.314, 17,353.17. That's going to give me 144,274.28 joule per mole. That's the activation energy, and that's how we calculate the activation energy. Let's see another example. the rate constant for the gas phase decomposition of N2O5. N2O5 is going to give us 2NO2 plus half of O2 and has the following temperature dependence. For 3 different temperatures in terms of Kelvin, we got 3 different values for K. Determine the activation energy for this reaction. It's very similar to the previous one. So let's consider the first one and the last one. So ln K2 or K1 EA over R 1 over T1 minus 1 over T2 ln, that's gonna be, let's consider this one as K2 3.5 negative 5 EA over 8.314 1 over 298 minus 1 over 338 based on the formula. So 1 divided by 298, 1 divided by 338. That's gonna be EA over 8.314. That's gonna be 3.97 times 10 to the power of negative 4. And here we have ln 4.9 times 10 to the power of negative 3 divided by 3.5 10 to the power of negative 5. That's going to be 140. EA over 8.314, 3.97 times 10 to the power of negative 4. EA over 8.314, you have ln 140 divided by 3.97 divided by 10 to the power of negative 4. That's going to be 12447.46. EA will be the multiplication of these two numbers. It's going to be 103,488.2 joule per mole. That's the activation energy. Let's see another example. The reaction CH33CBr plus OH minus gives CH33COH plus Br minus. In a certain solvent is in first order with respect to this one and 0 order with respect to the other. In several experiments, the rate constant K was determined at different temperatures. A plot of ln K with respect to 1 over T was conducted, resulting in a straight line with the slope of negative 1.1 times 10 to the power of positive 4K. So that means that's the slope. So it means that negative EA over R is negative 1.1 times 10 to the power 4 Kelvin. And y-intercept, again referring to this one, is ln A, is 33.5. Determine the activation energy for this reaction. That's simple. So EA is going to be 8.314 times 1.1 times 10 to the power 4. 8.314 times 1.1 times 10 to the power 4. That's going to be 91,454 joule per mole. That's the activation energy, the answer to the part A. Part B, it says determine the value of the frequency factor, which is A. Ln A is 33.5 as given as a y-intercept. So ln A is 33.5. It means that A will be e to the power of 3.5. That's going to be 3.54 times 10 to the power of positive 14. C. Calculate the value of K at 25 degrees Celsius. So, what we can do, we can say we have ln k equals to negative EA over R 1 over T plus ln A. We need to find out the value of k. Negative E over R, we have it, which is negative 1.1 times 10 to the power 4. 1 over T, T is 25. We need to convert it to Kelvin, so it's going to be 298. Plus ln A, which is given already, is 33.5. So 1.1 times 10 to the power 4 divided by 298. 33.5 minus 26.9125. So ln k will be negative 3.41275. K will be e to the power of negative 3.41275. K will be 0.03295. Per second is going to be the unit. So that's going to be the rate constant. Let's see another example. The activation energy for the decomposition of HI to H2 and I2 is 186 kilojoule per mole. That's the activation energy, 186 kilojoule per mole. The rate constant at 555 Kelvin is 3.52 times 10 to the power of negative 7. What is the rate constant at 645 Kelvin? So we have ln K2 over K1 EA over R 1 over T1 minus 1 over T2. So we need to find out the K2. K1 is given 3.52 times 10 to the power of negative 7. EA is 186,000 divided by 8.1314. 1 over T1, which is 555, minus 1 over T2, which is 645. That's going to be 1.8018 times 10 to the power of negative 3 minus 1.55 times 10 to the power of negative 3. So 6 divided by 8.12. That's going to be ln K2 over 3. This is going to be 5.6332. So K2 over 3.52 times 10 to the power of negative 7 equals to e to the power of 5.6332. That's going to be 279.55. K2 will be the multiplication of these two numbers times 3.52 times 10 to the power of negative 7. That's going to be 9.84 times 10 to the power of negative 5. That's going to be the rate constant for this example. Let's see the next example. It says a first order reaction has rate constants of 4.6 times 10 to the power of negative 2 per second and 8.1 times 10 to the power of negative 2 per second at 0 degrees and 20 degrees. What is the value of activation energy? 0 degrees Celsius, 20 degrees. So it's going to be 273 Kelvin, 293 Kelvin. So ln K2, K1, EA over R, 1 over T1 minus 1 over T2. So we have ln 8.1 divided by 4.6 because 10 to the power of negative 2 and negative 2 cancels out. EA over 8.314. 1 over T1 is 273 minus 1 over 293. So 1 over 273 minus 1 divided by 293. That's going to be this number divided by 831. So it's going to be EA times 3 times 10 to the power of negative 5. 8.1 divided by 4.6 ln of 1.76. That's going to be 0.5658. So EA is going to be 0.5658 divided by 3 times 10 to the power of negative 5. That's going to be 18,860.2 joule per mole. Or you can say 18.86 kilojoule per mole. That's gonna be the activation energy. I hope you enjoyed this video. Please leave me a comment if you have any question. You can find out lots of videos regarding chemistry, math, and physics in this channel. Thank you for watching and have a great day.